Today's webinar is Method Development and Maintenance for the QuickTrace M8000, presented by Jeff Forsberg. We will be taking questions at the end of the webinar, so please feel free to submit your questions throughout the presentation. Okay, Jeff, go ahead.
Good morning, everybody, and thank you for attending. This is a series of webinars that we've been producing at Teledyne Leeman Labs since late last year, and this is the fourth in the series. The previous one from the M8000 was QuickTrace software and how to develop methods in the software. So now I'm going to take it a step further, and I'm going to actually show you how we do it and how we change the timing to develop our methods. So with that, if any of you are new to the webinar series, I'm going to rehash some old stuff here real quick. So again, about Leeman Labs, we build mercury analyzers. As you all know, we provide choice of systems that meet your daily needs, and our systems are based on cold vapor atomic spectroscopy, with or without gold. We have two product lines, the Hydra 2 and the QuickTrace product lines, and they're designed to cover a variety of techniques and matrices and methodologies and so forth. Some of our customers include the environmental labs, wastewater treatment plants, academics, petrochemical, food, mining, pharmaceuticals, nutraceutical. Basically, if there's a lab bench, they're probably going to have a mercury analyzer on it, and they will have one of our products. So a little bit about cold vapor atomic absorption spectroscopy and atomic fluorescence spectroscopy. So in 1968, Hatch and Ott developed a commercially available atomic spectrometer. So it was an attachment to an AA that enabled them to take mercury at 2+ and reduce it to Hg0, and then those ground state atoms were sent to an optical cell for mercury determination. So this quickly became the choice technique for mercury analysis, basically globally, and then shortly after that, cold vapor atomic fluorescence followed. And by the late 1980s, there was some crude instruments out there that could be used commercially. And US EPA 1631 methodology was initiated in 1996. So that brings us up to today. So here we are. So we have the M8000 cold vapor atomic fluorescence system. Some of the highlights of this system is AF and AF gold, all in the same system. We have a patented gas liquid separator, superior dynamic ranges, as you will see as we go through this webinar today. QuickTrace software. We have a reduction in reagent gold trap costs, as I'll explain later, and we have choice of two configurations for automation products with the M8000. So the M8000 system, the detection limit is less than 0.05 nanograms per liter in the most sensitive mode. Realistically, the detection limit is around 0.01 or less, but we're all safe to say less than 0.05. US EPA 1631, 25 mils a sample. We easily hit less than 0.05 nanograms per liter for IDL and MDL. US EPA 245.7, 10 mils a sample, less than 0.1 nanograms per liter in 90 seconds. Our usable range is from 0.05 nanograms per liter to greater than 400 micrograms per liter. And we can do this without any hardware changes. So the patented gas liquid separator is a center post design, large reaction area to liquid volume, and what this will do for us, it gives us a increase in efficiency and it's increased throughput. It's a very fast system, and it's very stable. Liquid film flows give us reproducible signals and precise results. And this is in the low to ultra trace method detection limits based on this system. It's non-bubbling. If any of you are actual users out there, when you're running the system, it looks like there's nothing happening in the gas-liquid separator. You might be able to see a little bit of waste at the port for the waste removal, but it basically runs empty. Then there's no carryover and fast recovery. 1 ppm spike gets us back down to baseline in less than 4 minutes, and that's in non-gold trap mode, not in gold trap mode. If we loaded a 1 ppm on the gold trap, we'd have to do some gold trap cleaning. It's non-foaming, and that gets us biological samples like fish samples and so forth, so you don't have to add anti-foaming agents. As we know, if in a purge system or a sparging system, if there's bubbles or foaming, that can get up into the optics and that can cause a problem. So the detection system on this is a photomultiplier tube. We have a stabilized lamp. It's thermally stabilized in its own lamp compartment. And the carrier gas is computer controlled, and as we all know, argon only for atomic fluorescence. Nitrogen and oxygen will quench the signal, and we have extremely easy access to the gold traps, which in turn helps us with some of the maintenance. So it's basically you open the front door, and then from the front door you can grab the gold trap and pop it out, and you can exchange it and or inspect it before you start the system up. So the QuickTrace M8000 design is based on US EPA methodology 1631 and 245.7 and other methodologies that may be European Union or European norm type methodologies. Applicable methods typically or usually will require digestion. So any digestion, we're taking the mercury and we need to oxidize it, so it's +2 in the +2 valence, and then it's introduced to the system. You can either with or without automation. The systems can be manual. You can be the auto sampler and you move the probe from the rinse to the sample. It's really easy. So you digest the sample to 2+. The reduction of mercury to elemental mercury can either be with stannous chloride or sodium borohydride, and the light source is at 253.65, and it is measured at 90 degrees. So the M8000 is a valve-based atomic fluorescence mercury analyzer, and then that allows us to determine total mercury with or without gold or pre-concentration on either 1 or 2 traps. So the gold trap analysis, we use a cut time, and it's a state diagram within the firmware that changes the valves during the load or desorption type process. So if we look over here, we have valve 1. So when we're loading, when we start the system in gold trap, if you enable the cut time, the sample actually flows from valve 1 to valve 3 and then up to the detector. So we see a real-time peak. And once the air goes past the system from the probe moving, then we can switch the valves and load the gold trap. And that allows us to remove any ambient contamination from the air. There's a lot of mercury in the air. Outside, it's like 2 to 5 nanograms per cubic meter. Inside air, it can be up to 35 nanograms per cubic meter. So it's a fair amount of mercury within the air. So we don't want to put that on the gold trap. So that will help us get real numbers for what actually is in the sample and not in the environment. So it keeps our system more in control. So that's kind of a little bit about the cut time in the gold trap, and there's more of that in the manual. So the theory of operation is, so the acidified sample is introduced by a peristaltic pump, and again, it's got to be Hg 2+, and then we can introduce a hydroxylamine to pre-reduce the bromine monochloride or BRCL in the first mixing tea. And then in the second mixing tea, we introduce the stannous chloride, which in this case we use at 10% stannous and 7% HCl, and that's by a parallel channel on the pump, and then that is mixed there, and then from there it goes on to the reaction tube or the mixing tube. And by this time, it's almost instantaneous. So the stannous chloride reduces the mercury to Hg0 while it's en route. And then once it hits the gas-liquid separator, it's in a finely dispersed metallic type solution with excess stannous chloride. And when it hits the gas-liquid separator, it flows from the top to bottom, and then the carrier gas comes in the bottom of the gas-liquid separator. So at this point, it flows tangentially up and around the center post, and it very easily sweeps the reduced mercury off to the Nafion dryer, and then either directly to the detector for straight atomic fluorescence and or to the gold trap for amalgamation or enrichment. So it's a very efficient system, and it's very fast. So then at that point, once it hits the Nafion dryer, then the dried vapor, that's going to be mercury and argon gas, and then it goes off to the gold trap where it's collected on the gold trap, and any byproducts are sent through the gold trap, and they actually go off to waste, and then it's measured by the atomic fluorescence detector. And then ultimately the gas stream is going to exit the back of the instrument, and we collect it in a potassium permanganate trap. You can also vent it off into a hood or whatever you want, but it's once it exits the permanganate trap, it's basically clean argon gas into the laboratory, and then the byproducts are drained out and off to the waste. So a little bit about startup. So every time you start the system up, you want to inspect the pump tubing. So I lift the pressure levers, and I feel each tube for flat spots. The next thing you want to do is clean and fill the rinse reservoir. This is very important to keep for the shutdown process as well. If you don't do a lot of these things, then your system becomes not in control, and then you have to go through the process of troubleshooting, trying to source the contamination and get your system back into control. Once you have your laboratory in control, it's very important to keep that logbook so you know when new chemicals are coming in, you know what pipettes and vessels and everything that you're using to create standards. It's very important to log those, serialize those products, so you know which one you're using each and every time you make up standards, because if you don't have that audit trail, when you find your system is out of control, you can be down for 2 or 3 days trying to source this contamination and to mitigate it so you can get your system back in control. So enough about that. So the 3% rinse, typically we run 3% HCl for clean matrices. And if you're running matrices from industrial waste, let's say you're in that type of industry, or maybe even effluents or something in a wastewater treatment plant that may have some weird stuff going on, it may be beneficial to run HCl nitric acid in your rinse vessel, maybe a 5 to 10% HCl, 2 to 5% nitric, or something, whatever works for you, because sometimes the nitric acid will help keep things oxidized and help keep it a little bit cleaner than just the HCl. So the next thing you do, once you get your rinse ready to go, you want to inspect your GLS for cleanliness and make sure the capillary is set properly. Basically, if you look at it, it should look like it's touching the top of the center post, but it's actually, like 0.3 to 0.6 millimeters above that center post, but it looks like it's touching the center post. So then you'd want to start the gas flow. Ensure your tank pressure is at 35 psi for straight atomic fluorescence, or 15 psi for amalgamation. Since we have a valve-based system, we work with pressure, and we have flow restrictors within that valve-based system that change the flows throughout the system based on the choices you make within the method editor from high to low gas flow. And then it's also based on the pressure input side. So then you turn the lamp on, about 10 minutes warm up, that's all you need. And then once that happens, I start to strip chart recorder and I look at baseline signal. I want to verify that the system is steady and everything is ready to roll. And then inspect your liquid tubing tees, make sure everything's connected, empty your waste container, and then at this point you can lock the pump tubing into the bridge stops. Don't lock the tension yet, but you can put them into the bridge stops. And a rule of thumb is to use even pressure or even tension on both sides. So you pull evenly and lock them into the bridge stop. You should use this on any parasolic pump. Sometimes I see lab personnel hooking from one side and then pulling over the other side. That's not really a good technique because then you can stretch the tubing and then you don't get the correct wear and it can cause pulsations and so forth within the liquid stream. So you want to insert the rinse pump supply line into the rinse reservoir and then take the stannous chloride capillary and put it in DI water. We always start with DI water rather than stannous chloride because we need to wet the gas liquid separator. And if we do it with stannous chloride, then you can get a thin film of stannous on the inside of the gas liquid separator, which may hinder you from having a nice view of what's happening within the system. So we want to keep it pristine. So we only want sample over and stannous chloride over the center post. That's why we start with DI water, and I'll show you that in a minute too. And then ensure your rinse reservoir is empty. Park the auto sampler probe. That'll start your rinse pump, and it'll start the pull up of the rinse solution into the system. And then you can click on the startup icon within the method editor, which will set the pump and gas rates to that method that you already have open or will open. And then at this point, once the flows are going, you can engage the pressure clamps. Now they're all preset from the factory, so I always have this thing where you set it and forget it. So once it's set and your flows are correct, never adjust pressure on those pressure levers to compensate for tubing that is wearing out. That's just going to cause headaches. Change the tubing harness. It's very cheap. It's about $12 per tubing harness, and the pump tubing is going to last for greater than 100 hours. So, and then you inspect the liquid flows to and from the GLS. And then wetting the gas liquid separator. The patented gas liquid separator needs to be pre-wetted for a smooth, even delivery. So I place a paper towel or a Kim wipe up around the exhaust port, pinch the drain line right here. It's very easy. And then 1 to 2 bubbles to the top. That's all it takes to pre-wet that gas liquid separator. Release the drain line, allow it to drain out, inspect your flows to the GLS, and then from the GLS, and then you attach your GLS exhaust, which is actually to the Nafion, and then you're ready to roll. So now let's get into the method development. So what affects continuous flow with or without HG enrichment or amalgamation? So you have your gas flow, your pump rate, your time in sample, and in our case, we have the ability to set the PMT voltage. So that's on the table if needed. So quickly, the gas flows, high flow equals short resonance time. That gives you speedy results, but it decreases sensitivity. Low gas flows will increase the resonance time within the system and or detector. And the benefit to that is, one of the negatives is longer times, but the benefit, it increases the sensitivity. You increase the sensitivity, you decrease your MDL and your IDLs. The pump rate will increase or decrease the time to the GLS and or the mercury load onto the gold trap. So then the time in sample will also increase or decrease sample load. So we adjust this to a steady state for a signal plateau without gold enrichment, and with amalgamation, we use it to increase or decrease the dynamic ranges of the system. And then additionally, like I said, we can adjust the PMT voltage to decrease the sensitivity. So you want to adjust all 3 or 4 depending on your desired results. GLP, so we always wear gloves and you clean as you go all day long. And I use a very simple technique for preparing standards. So it's, I call it the lid on, lid off technique. And I start with the blank and I continue from the lowest to the highest. So I'll add my makeup, whatever I need to bring it up to volume. Could be a weak acid or so forth. And I add my aliquot of working standard, and I use large additions to create that working standard. So what I don't do is take 100 microliters of some stock standard and add it to 100 milliliters or a liter of some matrices, like 3% HCl or something like that. I would use large addition like 1 mil into 10 mils, and then I take additions of aliquots of that to produce the working standards, which I'm going to use for the calibration standard. And typically you want to try to use one working standard to produce all your calibration standards, so you have one continuous line, because if there's any issues within this process, you can have a break in the line and you can actually see where the curve may change if you switch from one standard to the other to produce your standard. So I'd always work it out on paper first and make sure it's gonna be conducive to what you want to achieve. Then from that point we add the digestion reagents. Now let's get into the method development. So method development, let's start out with 0 to 100 nanograms per liter in non-gold trap. So we have CAN methods within the system, and the naming of the CAN methods kind of guide you toward what they are and the autosampler that you're using and so forth. So here I just picked high sensitivity because I know that that's not with gold and it's just straight atomic fluorescence, and I enter my standards. So I'm going to enter 5, 20, 100, 500, and 1,000. You know, is that going to work with this CAN method? I'm not really sure, but let's give it a go. So when you become experienced, you really know your system, and you can take and tweak a method within a matter of minutes, do a peak profile, create this method for that system, for that method that you want to run, and away you go. So what do we do? So we're going to peak profile the high standard, and the systems are pretty forgiving, so I don't really worry too much about what happens to it, because the carryover is very minimal and it's got a fast recovery if you happen to make a mistake within the system. So you just kind of go with the flow and make it happen. So here we open this up and the pump speed's 100%. The gas flows at low flow and set to 35 psi because we're non-gold trap. Integrations are 4 replicates times 4 seconds over here, so that's 16 seconds total integration time. Our rinse time is 100 seconds and our uptake is 60. Is this going to work? I don't know, but let's give it a try and see what happens. So once you develop these methods, it's always nice to use smart rinse too afterwards. And what I do is I look at the response of the highest standard, add 10%, and then enter that into the program. So I peak profile this using the CAN method, and the signal is relatively steady, and it kind of matches the timing parameters. So we've developed these methodologies, so the CAN methods make it easy for you, but so it's pretty close. And I look at the response, and my response is 800 HF units or thereabout. My nonlinear begins about 4,000, so that tells me that 35 psi low flow is going to work for me. So I'm going to leave it at that because it's about 1/4 of the target. The pump rate seems to be good, so I'm going to leave that. And the signal is not too bad. It's at 35% RSD, which is good. Anytime you're above 100 nanograms per liter or so, your signal should for sure be less than 2%. So I always strive for less than 0.5%, and you can tweak your method to adjust those signals as well. So should we remove some rinse time in this? Since it was quite flat and quite long, let's give it a go. So let's take and go from 80 to 100 to 85 seconds. What about the uptake? Should we leave it at 60? Should we change the peak integration? It seemed like it was a long flat plateau or somewhat. So right here, when I make these changes, I can do it in real time right in the method editor, and I can see the effect. So we got cause and effect right here. So I changed it to 2.5 seconds. So now we have 4 times 2.5, so we have 10 seconds of integration, and I moved my read delay and so forth, and so my integration percent RSD went from 35 to 0.19%. So it got better, and you can change your baseline points. That's one of the beauties of this system. Let me go back real quick. So you see everything here is performed in the method editor page, and you can make all these adjustments in real time, and you can see the effect it has on your method development, so it saves time. So with that, I noticed that I changed the read delay as well, and I changed the, like I mentioned, the integration time. First baseline was okay at 10 seconds. It's before the signal quench. Second baseline, I changed slightly, and then the rinse from 85. And I'm going to leave the uptake at 60. That's not really going to give me a huge benefit at this point, so I left it at 60 seconds. So then I'm going to peak profile again to validate. So once I did those changes, my percent RSD went to 0.19, and then when I do an actual peak profile with the new changes, it came in at 0.01%, so it's almost flat. Can't really improve too much on that. So the gas flow at 35, uptake at 60, post signal base is at baseline, so I'm just going to leave it. So let's go with this. We need to trust but verify. So I'm going to ensure that the standards I've chosen are entered in. So I'm going to run with a blank 5, 20, 100, 500, and 1,000 nanograms. I'm going to generate a sequence with 0 sample count because I want to enter in my standards manually as rebacks to validate the entire method. So one more check. It's always nice to read the blank. Make sure you don't have any contamination. And your integration should be out of the quenching. So over here is the quenching. That's when the air goes through the system. Normally on a clean system, it might be anywhere from 0.2, 0.3 negative up to maybe minus 2 HF units. That's a clean system. And we'll talk about this later in the troubleshooting section. So this looks like a good rinse, so I'm ready to go. So I'm going to run my calibration, and then I'm going to look for trouble spots during this calibration. So it turned out that I achieved 4 nines and a 0, which is relatively good. The slope is 0.87, 264 HF units per PPT, or nanogram per liter. My intercept, when you can zoom in on these too, so you can also get a closer view of the graphs. All the graphs and everything in the systems, like I mentioned, are real time and user interactive. You can interact with these UIs and move, zoom in, zoom out, adjust left to right, and so forth. So the intercept is at 5.96, which turns out to be, when I run the math, it's 0.68 nanograms per liter. So that's not too bad, and the R squared is 4 nines, like I said. So now I'm going to read the readbacks, and what I do is I like to mix them up a little bit, because if you mix them up not in the order they were calibrated, but just kind of randomly put them in there, it'll tell you more about the method. So I ran the blank, and then 100, 20, 500, 5, 1,000. Then I put the blank in at the end. And this will talk to me about the carryover and so forth within the system. So it's not too bad. It came in at minus 0.9, 97, 19.5, 497, and 3.8, which I'll discuss, and the 1,000 came in at 1,010. And I think that's pretty good. And the last blank after 1,000 came in at minus 1.1 nanograms per liter. Again, we are calibrated up to 1,000 nanograms per liter and or 1 ppb. So that's the calibration side. The more important side is the response. How is the system behaving based on the response? So that's a telltale sign about the system, whether it's in control and everything is in good shape. So if the readbacks give us the same response as the calibration, that tells us, one, the system's functioning properly, and any issues with the calibration is on me. It's not on the system, it's on me. So it's my inability to create a perfect calibration or a calibration that's going to be conducive to my desired results. So in this case, the readbacks, I pulled for easy access or easier view, and I pulled them up and put them up here. So we have minus 0.09, minus 1.5, 4.38, 3.89, 17.6, 17.5, 85.5, 86.7, and 434, 443, and 879 and 870. Those are pretty much on top of each other. So that tells me the system is in control, it's working nicely, and basically we're ready to do an IDL or MDL with this method. So a little bit about the method. So the blank following that 1,000, that showed a slight negative value, and that's because there was a little bit of carryover. So if you look over here on the graph, you can see it right here. So that elevates my baseline slightly, and there was a slight drift in the signal response too, but it's not really out of control. It's going to be fine. Most of it is coming from the small amount of carryover, because again, we're going from 1,000 ppt down to 0. So if I would take and increase that rinse that I took out 15 seconds and go back from 85 to 100 seconds, that would normally fix that issue. So that explains the rinse, and it's going to explain that 5 ppt as well. If you recall, that was like 3.8, so slightly below the mark of 5, and here it is again. It shows a slight carryover, so if I added 15 seconds back in here, I'm going to be more in the flat spot, and then that's going to eliminate that, because the way it performs the baseline correction point, we're reading from here to here, and it's drawn a line. So if it's elevated, that's going to remove some of the signal from my response and give me a lower result. So again, the rinse, adding the rinse back in would fix that. So over the range of 0 to 1,000, it exhibited a pretty nice linearity, but can we make it better? Well, yeah, the broad plateau, could we remove some time? Maybe we could go down to 55 seconds, but in the broad scheme of things, 5 seconds is not going to make that big of a deal unless you're running hundreds and hundreds of samples. You know, you're running a couple, 300 samples a day. 5 seconds is probably going to turn into some real dollars at the end of the day, but that's not my call. Personally, I would probably leave it in. Additionally, we could have maybe went force through blank. That's on the table as well. That may have given us some slightly better numbers too. But again, when you look at those readbacks from that 0 to 1,000, they were all pretty close and probably very conducive to a nice method and more than acceptable to a quality control manager in any lab. So the best option to improve, in my opinion, would be to add the seconds back in and leave the uptake the same. So we'd be looking at 160 seconds per sample. Additionally, you could achieve a 1.0, but that is difficult to reproduce each iteration of calibration. So maybe that's not a realistic option. But 1.0 is 1.0 for the calibration is very doable with these systems. And then additionally, it's very important to matrix match the systems. Trace analysis from 0 to 100. So let's follow the same process, and it's always best to bracket your unknowns. So if you're going to read below 10 or below 100 or so forth, it's best to run a calibration from 0 to 100. US EPA 245.7 in this methodology, IDL 1.8. Very easily doable. So we want to follow the same process as I showed you for the 1,000. So here is the final method for this one, so pump speed 100%, gas flow 35, and the uptake and rinse are pretty much the same as the 0 to 1,000 calibration. The timing's a little bit different, so 64.5 seconds to read delay, and now I'm going to use 16 seconds of integration rather than the 10 because I want to have a really good clear vision of the top of the peak because we want to read extremely low. Analysis time, so it's 2 minutes and 40 seconds, and then the 100 nanogram per liter peak profile came in at 0.23%. So in this case, I calibrate with a 1, 5, 20, and 100. My readbacks are going to be 520, 1, and 100. So again, I mix them up. So the readbacks, the blank came in at 0, 5 came in at 4.9, so that's better than 3.8, which was in the higher calibration. But again, it's a tighter calibration, so that reduces some of the error and gives you a better shot at getting a good calibration. And in this case, the correlation R squared was a 1.0, so that's as good as you can achieve with the system. That's why all the smiley faces. So the 20 came in at 20, the 1 came in at 1.1, the 100 came in at 99.7, and then my blank after that came in at 0.1. So basically, there's no carryover on the system. Readbacks, let's look at the HF units. So we have minus 1, 0.01, that's pretty insignificant, 0.7992, 4.4, 4.4, 18.2, 18.2, 90.9, and 91.2. Basically the same, which again tells me the system's in control. So over the range of 0 to 100, it exhibited perfect linearity. My total method time was 160. The readbacks were almost perfect. So again, we'd be easily able to meet 245.7 criteria with this system, as the 1 nanogram calibration value is 0.79, and that's very discernible above the blank. So if you look over, here's the blank, here's the 1, that's a very nice signal. Even with this system, we could possibly meet the EPA 1631 under performance base without using gold trap. I don't see any reason why it wouldn't work. And again, it's very important to matrix match. So calibrations up to 500 ppb. So again, let's get out of the nanogram per liter mode and get into microgram per liter mode. So 500 ppb is possible. It's not a misprint. So to analyze concentrations below a 1 ppb, I recommend the use of trace type mode. And we're going to follow the same process of reading the high standard and read the blank. You've got to remember now that 400 fluorescence units, or in our case about 4,000 HF, we kind of get into the nonlinear range. But high calibrations can be set up for speed, and we can do this really, really fast. So I'm going to open up the normal range because I know that is under high flow, 35 psi, pump rates is set at 50% and so forth. My uptake, I'm going to remove it from 30 to 5 seconds, so my total analysis time is going to be 35 or 95 seconds. I'm going to take my peak mode and change it from peak height to peak area. I want to peak profile and adjust and calibrate. So over here is those standard settings. I just read it. I left them the same, so here's the integration point, but it's still changed to peak area. So again, while you're in this mode, it's real time, so I can take and move my timing parameters, and I can see what effect it's going to have on the peak. So the pump rate looks good. Gas flow is high flow at 35 psi, approximately 225 mils a minute. Uptake is 5, which gives us about 0.5 mils of sample. Total analysis time now is 105 seconds. My integration is 44.5 seconds. So I start my integration at 34, end at 44 or 45 seconds later. So here's my integration, and here's my baseline. So the signal is within the linear range, but it's on kind of the edge of it because we're at about 4,000 units. So let's take a look and see what happens. So we'll do a calibration. I'll run a blank 10, 100, and 500 ppb, micrograms per liter. My correlation comes in at 3 nines and basically a 6 if I round, which is acceptable and it looks okay. So I'm going to read my blanks back, 10, 100, and a 500. They come in at a blank is minus 3.6 ppb. My 10 comes in at 8.5, 100 is 110, and 500 is 511. That's not bad. Again, we're in ppb mode in a atomic fluorescence system. Let's look at the readbacks. So the blank is 0.19, so that's basically 0 like over here. The 15, or the 10 is 15, and here 15.7, 15.4. The 100 is 146, 150. The 500 is 665 and 681. Relatively the same. So it looks okay, but let's see if we can improve. So now when we look at the calibration and we zero in on it and zoom in, I can actually see that the 500 looks a little bit low, and if I calculate it, I'll normalize it to the other two, the 10 and the 100, which are linear, at 15 and 115, normalize it up to 750 to get a 1.0. So that's one of the drawbacks of getting into that nonlinear range. So, and if I wanted to correct for that, I could do a quadratic fit, which would help compensate for that. But again, even running linear up to a 500 ppb with this system, 3 nines is more than acceptable for the system. So total method time was 105 seconds. Increasing the rinse may have helped with that false negative on the extreme low end. The readbacks were acceptable. The 500 was slightly low, which skewed the low end, so linearity, quadratic might have fixed it. And then again, it's very important to use matrix match standards. Let's get into the gold trap analysis. So again, you grab a method, and UltraTrace or ultrasensitivity I know is with gold traps, so let's enter the standards in at 5, 1, 2, 5, and so forth. And again, once you know how to do this and you've done it a couple times, it's really, really fast. So if someone comes down to you and says, I want this method, I want to run up to this calibration, you just, yeah, I got it, I can do it. So again, we peak profile, the pump speed is 100%, gas flow is at 15 psi, low flow. Here's our integration time and read delays and rinse time, and our uptake is 160 seconds. And you got to remember in gold trap that your rinse plus uptake must be slightly longer than your last event. And here our last event is heater stop time at 4:45. So what are we going to do for our baseline correction point? Start and duration, end and duration, so forth, for both 1 and 2. So I just did that CAN method. So open it up, run the peak profile. Gas flow gives us approximately, our peak height is around 1200, so we're a fourth of our target, so we're within linear range, not a problem. So we can leave it at low. We can leave our pump rate where it is because our load is just going to be perfect. Again, less load, you're going to decrease your sensitivity. The peak start baselines need some adjustment, so we can zoom in on that and do some quick tweaking. And again, it's all real time, so it changes right here. This is our real-time peak prior to the cut time. Earlier in the webinar, I talked about the valve switching. So this is a real peak, the mercury coming into the system right here, and then it goes to the gold trap, and then the gold trap desorbs off the system. Desorbs the mercury off the system. So validate the method timing changes. Peak start, I'm going to change it to 265, and again, it's real time. The peak width is 120, that's fine. And when I look at the baseline, I try to keep the end of the peak integration at 1% of the peak height or below. And I adjusted my baselines from 245 to 255 in here. And then my second baseline, and then again, the cut time, you can zoom in to make sure that this is the probe movement, that's air ingestion into the system. You want to have that outside of that time. Heater and rinse times are okay. So let's go ahead and repeat the peak profile for verification, and then we'll read the matrix blank to spot any potential issues. So I generate a sequence, 0 sample count to validate the calibration. And this is going to include the entire system, which includes the laboratory. My R-squared is 3 9s, and I think that's okay. Most methodologies require 2 9s and a 5, but my blank's a little bit high. It's around 3,600 HF units, so I have a spreadsheet, and I can pop all the values into the spreadsheet. And for 1631, so this actually wasn't calibrated in 1631. And I'm sorry, but I might go a little bit over, so if you guys bear with me on the time, we might be a little bit long on 60 minutes or an hour, but this is good information. So please hang 10 for a while, and we'll finish up the webinar. So again, the US EPA 1631, it fails. So my 3 blanks, when I normalize them, it comes in at 1.1. The CF factor fails miserably, and the 5 repeat comes back at 157%. So this totally failed. But the RSD looked fine. So, but again, 1631 is kind of a different animal. So we'd assume it passed, but along close inspection, we can see where I have contamination down in this low end, and that was causing the problem. So I'm going to go ahead and clean the standard test tubes and so forth, and try to renegotiate this calibration and get everything back in control. So I redo it, and I come up with 4 9s and a 7. It's much better, but will it pass? So after the cleaning the tubes, the calibration would pass. So I pop them into my spreadsheet. I normalize the 3 blanks. They come in at 0.42. My percent RSD on my CF factor passes, and the recovery of the low standard to 5 comes in at 106%. Everything's good. So this actually would work for 1631 if all my blanks would pass when you read real blanks, and they should. So run back calibration. Let's look for some trouble spots. So the slope on this is 28.41 HF units per nanogram, and it's a good slope, and it's a nice response. Intercept is 1,365, which turns out to be 0.48 nanograms per liter. So it calculates in the EPA methodology at 0.42. It all passes, and the R-squared is good, and the CF factor, it all passes. So let's trust but verify. Let's take a look at some of our readbacks. So after the 100 nanogram per liter standard, all 3 readbacks were around 1,300 or 1,400 units, virtually the same as the calibration blank. They came in at 0.0. So 1, that tells me I don't have carryover. That tells me, again, that no carryover, my gas flows, my pump rate, all that is conducive to a good method. So I'm ready to rock and roll. The 1 came in at 1.2, 2 at 2.0, and the 100 at 99.4. Let's look at the responses. So the average response was 1,403, which is virtually the same number. The 1 came in at 4,705, and we have 4,739, basically the same. The 2 is at 6,900, 7,100, basically the same, and the 100 came in at 284,000, 286,000. So we got nice responses for the system, so it's in control, and we're ready to roll. Blank checks. So again, they didn't exhibit any carryover, so I think my system is giving me the desired outcome, so I am ready to run a 1630 calibration and or do method MDL or IDL study, depending on what you want to achieve with the system. Now, let's look at 0 to 10 ppb in GoldTrap. Yes, ppb, we can do this with the system. So again, GoldTrap method, I open up the ultra trace. So I'm going to enter my standards of 0, 1, and 10 ppb. Is that going to work? Yeah, maybe it should. I know we can do this. So what can we do? We can adjust the PMT setting. So that's on the table. So if we change the PMT setting, that will reduce the sensitivity of the system. Purge gas, low flow at 35 psi. Is that going to work? I don't know. Uptake, I know 160 seconds is going to be a lot of mercury onto the gold, so let's reduce it. Let's go to 20 seconds. Let's change our rinse time to be conducive to that. Start trap of the gold trap heater on and start time. So what I'm going to do really quickly is, since I've taken that time and I've moved it to 20 seconds, I'm going to move my peak start time to 95, and I'm going to change my baseline, my gold trap turn on time at 60 seconds, and then my second trap, which is a blank tap, we always run that for about 60 seconds just to make sure that no mercury hangs up in the system. And then I'm going to do a peak profile. So there's, again, after the 20-second uptake, I like to have approximately a 40-second wait time before I turn those heaters on right there. So I don't get a peak. I have a very small peak. And did it tell me anything? Well, it kind of did. It told me that, one, if we look at the peak height, it's at like 1500. I know it's like a 10-to-1 ratio in the non-peak to the gold trap peak. So that tells me that low flow on 35 psi is not going to work. So right there, I moved it to high flow, and it told me that there's an issue with the cut time, which I anticipated that there would be. And here's actually what happens. So time 0, the valves are going from B over to here to the detector to give us that real-time peak, and then at 20, B and 3A go to waste. So then at 40, where I had my cut time, it went from B to A for 1 second, but we stayed over here in this zone. Therefore, a very small amount, 1 second worth of mercury, was loaded onto that gold trap, and that was during the wait time. So that's not going to be my true value. So that gave me an indicator that I need to disable the cut time and change the gas flow to high. So I did that, reread the peak profile, and voila, got a nice peak. Here it is at 1500 or 1600 units in height. I'm below my nonlinear, so I'm in good shape. The peak starts at 120 seconds. The peak width is 120 seconds wide. Everything looks really, really good. So now I can adjust my integration for my baseline correction points. I can put those in there. And I looked at the baseline, and I added a little bit of time to 310 seconds because 20 plus 310 is 330, and that was my last event. Was my second gold trap was turning off at 225. So it works really well. It looks nice peak. So reducing the PMT seemed to work. So now we have a 0 to 10 calibration. I'm going to enter a sequence. My R squared is 1.0, but again, I only have a 2-point curve, so it's not a real true test, but it's a good indicator that the system's going to work. My slope is 33,000 units per ppb. The intercept is basically 5 ppt, which is really good. And again, I got a 1.0. So let's read back the samples. So my 0.1 came in at 0.01. My 10 came in at 9.95, which is good. And the blank came in at 0.1. So then let's look at the readbacks. So the readbacks are, the blank was 339 and 149 was the original. The 1.1 came back at 3,561. The original was 3,465. That's good, or the calibration. And the 10 came in at 325,000 versus 326,000. So that tells me, again, the system is functioning properly. It's given me the response back that I indicated. So yeah, the correlation is probably valid, and the system's in control, and we should be able to use this as a method. A little bit of discussion. So this blank right here, if I run a little bit of math on it, subtract the 149 from the 339, that gives me 0.06% of the 10 ppb as carryover. So that's pretty insignificant, so I'm not going to worry about that too much. Again, we're calibrated up to a 10 ppb. We're not in PPT mode, we're in PPB. So again, this method is ready to run high calibrations for high samples, and this may be for research or anything that's outside of, 1631 type methodologies. Very good and very forgiving system. So again, we have from ultra trace to sub ppm or high ppb range modes. Shutdown, a little bit about the shutdown. So basic shutdown, you place your stannous chloride capillary in 10% nitric. We want to rinse for 10 minutes, remove the rinse from the rinse reservoir, so we want that section to run dry, so on the autosampler pump. Then after that, we want to rinse our stannous chloride with DI water for a minute and remove it. We want all this system lines to run dry. So let everything run to dryness. Raise your probe, then disconnect your Nafion from GLS, turn your lap on. If you're not going to be using the system, you can do a complete shutdown if you're not going to use it in the near future. Wait till the waste lines clear and run empty, and then you want to release and relax your pump tubing so it's ready for the next run. Always release that pump tubing, and by relaxing it, remove it from those bridge stops. You're going to avoid flat spots on the pump tubing, and it's going to make it conducive to 100 to 200 wear hours per tubing harness, which is really, really good. For the GLS, you want to make sure this is clean all the time, but it's pretty forgiving, so don't worry about it too much. The basic shutdown is going to go a long way to keeping this thing clean. But if you need to, you can do an online cleaning, 50% nitric, 20% HCl, and or DI water to clean online. And remember, daily shutdown goes a long way to keeping your system in control. And like I have to reiterate about keeping serialized numbers of your pipettes and different apparatus that you're using during this process. Keep everything in control. Basically, play the 2-year-old and say, mine. So it's mine. Nobody else can use it. So other metal departments like the ICP-MS, I'm not picking on those people, but ICP-OES and so forth, they should not use anything that's deemed mercury. So if you label it, keep it in control, keep it with your method for mercury analysis, and it'll produce a lot less headaches. So offline cleaning of the GLS, immerse it in 50% nitric in a vessel that's going to keep it so it doesn't break. Here it actually fits in a 50 ml test tube. Rinse it or sonicate it for 30 minutes, rinse it inside and out. I put a small pipette tip on a squirt bottle, gets the inside. Repeat that sonication with fresh acid and rinse. US EPA 1631 analysis, typically I suggest a clean GLS every time you run. So when you're running today, you're cleaning your GLS that you're going to use tomorrow. So you leapfrog it into the system. And that's one of my earlier webinars. I talked about sample prep and cleaning test tubes and testing at a 10% rate, and the leapfrog method of testing today what you're going to use tomorrow for test tubes and so forth. Pump tubing, inspect it daily. It's pretty robust. It's going to last for 100 hours. Always install into the bridge stops with equal pull force. Replace the full harness. Don't just replace one tube you think is bad because you're asking for problems. So replace the full harness. Ensure that the tension stays correct. Set it and forget it. Don't adjust it. Just let it go. Change the tubing harness if you spot problems with the pump tubing. The bottom three pressure levers are this in on their standard setup are all the same tubes, so they should be equal in pressure or tension, and the top one is a smaller tube, so that should be about 1 millimeter further in. Again, it talks about in the manual how to set the tension and the pressure on these tubes, and then so once it's set, you just forget it, don't do it again. Changing the lamp, it's pretty easy. So we have the new detector in 2014. So you open up the cover to the system, you locate the lamp in the back, you unplug it, you remove the lamp housing, loosen the 0.05 inch cent screw, and you pull the lamp out, install the new lamp, make sure that the scribe is in the 12 o'clock position, tighten down the set screw, close it all up, and you're ready to go. It's pretty easy. It takes about maybe 5 minutes to change a lamp. It's that simple. Everything is very accessible within the system. We wanted to, when we developed the system, we had the customer in mind, which is why the gold traps are up front, easy exchange, easy to inspect prior to the run. Same thing for all the internal systems. Same thing for the detector cell, but again, wear powder-free gloves when you're looking at this, and it's very rare you have to do anything with this. But if you do, you want to keep it in control and put it into like a test tube, sonicate it for 30 minutes with 50% nitrate, rinse it inside and out, again, pipette on a squirt bottle, and then secure it, make sure it's not going to break in that container, like I said, and then repeat that with fresh acid and rinse. And then connect it to the supply gas on the front of the instrument by the GLS, and you can dry the inside. And then the outside you need to clean. And we use IPA, cotton swabs or foam swabs. Never dip into the bottle. Always pour out the IPA into a disposable beaker, because you can contaminate the IPA if you do it the other way. And also, then once you put the system back together, if you have problems, it's hard to source where that problem is. And then you can use the gas from the supply out front to blow off any fuzzies from the outside of the detector cell, and then put it all back together. Contamination within the system. So that quench, that tells us a lot. So here we have a large quench, so that tells me that I have problems with the stannous chloride in the system, because when it zeros, everything is flowing, continuous flow. So again, that quench should be very small down here, maybe 0.2 to 0.2 units. So that's a good quench. Higher than that, we have a contamination issue. You can see it in the gold trap. You can see it in the non-gold trap. So if you observe this system while you're doing your peak profile, that will eliminate a lot of headaches before you get into actually trying to calibrate the system. To try to source some of these contamination issues, you can bypass the GLS and take the GLS supply and go right to the sample end, so you can read your gas. Your gas should, in mercury analysis mode, should be just, less than 100 HF units in area. If it's higher than that, you want to clean your external gold trap, and you can also install, we have a purification trap that you can install upstream from your external gold trap. So what I do each day that I run ultra trace mode, I pop my gold trap, external gold trap, into the system and start my oven and strip chart recorder, and I look at the peak coming off. There shouldn't be any peak. With using the purification trap, that eliminates the mercury that's in the argon, and there's a lot of mercury in the argon. 4,900 tons approximately every year up in the atmosphere. Where do they get the argon? They distill the atmospheric air and make your trace gases, your argon, your nitrogen, helium, and so forth. So all that mercury in the air goes into the argon. So yes, we need to keep it pure. Otherwise, in gold trap mode, you're going to have false positives from the argon gas, and this can be transpired into other analytical techniques as well, where you're looking at mercury. So aqueous side of it, so what I do is I eliminate the auto sampler and I connect the probe directly to the pump. And then I move the probe between the rinse and whatever sample I'm testing. So then it tells me right there and then what's contaminated. So I want to take the auto sampler out of the system. But again, the auto sampler, you want to have clean rinse pumps and make sure your rinse your rinse station is clean, and all that should be clean all the time. But if you do this way, you can zero in on the contamination really fast and look for the quench. Also during gold trap analysis, so if you do the same process, you can see where your contamination is coming from in the rinse, the makeup standard, the stannous chloride, and so forth. You can see where you need to address the system to keep it all in control. So that's kind of how I do the troubleshooting. And if there's questions on troubleshooting and how to source contamination, by all means, give me a phone call. We can go through it in depth more than on one slide in a webinar. So again, I'm sorry for the overage of a few minutes, but hopefully it was worth your time. So the QuickTrace system, method development, my opinion, quick and easy. It has an amazing group of dynamic ranges. I mean, really, we're talking trace analysis, sub-PPT to sub-ppm analysis on the same system. I don't believe there's any other system on the market today that can achieve those dynamic ranges. The manual is easy to read. There's lots of pragmatic tips in there on method development, and we have a good extension in sections on maintenance, daily, monthly, and yearly within the system. So here's a little trailer. Theory, method development, maintenance for Teledyne Leeman Labs, Hydro 2C, mercury analyzer, direct combustion.